I've got this. So, welcome, ladies and gentlemen. Today we are talking about limits, and we do have some familiarity with limits as n approaches infinity. Back in the day when we were doing infinite sequences and series, and we were able to find the sum of an infinite series using limits. Today we are going to talk about limits not when our variable approaches infinity or negative infinity, but when it approaches a particular number. So for instance, what happens as it approaches 2 and gets infinitely close to it, right? What is the function approaching at the same time? All right, so that's what we are talking about today. The first thing I'm going to do, well, I guess I'll throw this down here. I'll grab a little snapshot of this. I'm not even going to have you write it. I just decided right now to even put it in. But I'll give you the definition of a limit of a function. Man, that's a little bit blurry, and my buttons aren't working. That's okay. Close enough. And no, that's terrible. All right, I'll let it focus. Here we go. Here we go. Focus, focus, focus. Enhance. Here we go. Definition of a limit. And like I said, we've already seen limits before, so don't write this down. Do not. We're going to have a really clear understanding of limits just from our application of them. So it says, if there is a number L such that the value of f of x gets closer and closer to L as x gets closer and closer to the number a, then L is called a limit of f of x as x approaches a. Okay? Sure. So I'll take the limit of some function as x gets closer and closer to a particular value. So let's talk about this from a graphical sense. Let's do some examples here. Actually, I might make a crazy looking graph, and then we'll talk about the limits of different points on that graph. So this is going to be a wide graph, and I'll actually try to 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and 6. And actually, the y values I don't really care as much about.
You don't care about y?
No. So let's do this. Suppose I've got this situation. All right, and suppose I've got one of these, maybe like that. So that's at -2, and then we'll have one of these. And then we'll have it suddenly do one of these. And one of these. This is the best roller coaster ever. Yeah, draw this roughly as best as you can. And there we go. Look at that awesome roller coaster.
Teleports everywhere.
Yeah, good stuff. I imagine that x equals, well, I don't know, which would have a greater jerk in the ride. I would say x equals 1 would have like a sudden like instant back and forth. Although going from infinity to negative infinity, I imagine, would be a sudden shift in momentum.
I know what it is. It's a roller coaster that runs through all the doors from the movie Matrix Reloaded, you know, where the guy can open a door, closes it, then the guy comes in and he's in like the Outback or wherever.
Yeah, I do like the idea of considering asymptotes that have this behavior to be somewhat portals. It's pretty good stuff. So, all right. So let's take a look at this. So here's my function f. All right. So function f. There we are. So there's a graph of it. I don't feel like making a chart for that, and I also don't feel like defining it as a piecewise function because it's got 1, 2, 3, I don't even know what this is, 4 pieces. And actually, no, well, 5, including this point, because I'd have to define it for that particular value.
2 separate in order to get the 3.
Well, this might be a single polynomial. It could exist. But anyways, regardless, let's find the limit as x approaches let's start with something easy. 1, 2, 3, 4. Let's find the limit as x approaches 4 of f of x. So what we're asking is, what does this function approach as I get close to 4? So as I get close to 4 from the left and right, it appears to be approaching 2-ish, right? For the height there. So the limit of this point is 2. Now, question, is it continuous at x equals 4?
Yeah.
Yeah, because it exists at x equals 4, and it approaches 2 at x equals 4 from both left and right, and the thing that it approaches from left and right is the thing that it exists at x equals 4. So it is continuous there. All right, so there's our first concept. Let's find the limit. What if I find the limit as x approaches 1 of my function f of x? So from the left, I appear to be approaching, I'll call it negative 1.5 maybe. And from the right, I appear to be approaching negative 1.5. But at that point, I appear to be 2. So is it continuous at that point?
No.
No. But if I was concerned about just the limit and what I was approaching, what am I approaching as I get...
approaching negative 1.5.
I'm approaching negative 1.5, right?
I get there. But you're
I never get there. But limits are only about what we are approaching. So even though it's not continuous at x equals 1, because it fails... actually, what part of the continuity test does it fail?
1. No.
No, it exists. It approaches, it fails part 3, right, of the continuity test, just to gain our familiarity with that. But even though it fails continuity, the limit does exist, because it's approaching the same thing. All right? What about the limit as x approaches negative 2 of my function f of x? Now, from the left, this appears to be approaching 1. And from the right, it appears to be approaching 3. It exists there. All right, so just in terms of review, is this continuous at x equals negative 2? No. What part of the continuity test does it fail? 2 and 3 by default, right? So it exists at the point, so it passes part 1. It doesn't pass part 2 because it's not pointing towards itself, right, from left and right. It's going to be an agreement. And then it fails part 3 by default. So it's discontinuous. But discontinuity wasn't a problem for us a moment ago, right? A limit existed here. But what do you think about the limit here? As x approaches negative 2. I mean, from one side it's approaching 1, the other side it's approaching 3. It turns out the limit does not exist. DNE. Because it would depend, right? It would depend. Am I approaching Brattleboro from New Hampshire, or am I approaching it from Vermont side, right? Like,
But you'd still be approaching the same point. This is like approaching Brattleboro from the Vermont side and then Bennington.
yeah, I suddenly it's approaching, it's trying to get to the same point in terms of the x, but then my y values suddenly are in different locations.
You're like, no.
It'd be weird, yeah. So it doesn't exist. However, you won't have any problems like this in this section, but subset problem right here. 2 little problems.
I thought those were LD.
No. If I want to find the limit as x approaches negative 2 from the left, I can put this little exponent of a minus sign up there. And what is the limit as x approaches that from the left? From the left, it's approaching 1. That limit exists. And if I want to know the limit as x approaches negative 2 from the right, I'll put like a little plus sign in the exponent. And what is it as I'm approaching from the right? I'm approaching 3. So these are kind of like partial limits, I guess, where I'm just concerned with one direction. And those do exist. I don't think we end up dealing with them in the rest of this course. You might see those later on in calculus, though.
Two to the positive and two to the negative.
Yeah, that's read as the limit as x approaches negative 2 from the left of f of x is 1. All right, so just so you're aware, I figured that's something kind of interesting to point out. And, of course, the next thing I'm going to ask about is what about the limit as x approaches negative 4 of my function f of x? So here this is approaching positive infinity, and here this is approaching negative infinity. It is not continuous at that point because it doesn't exist at that point. Your left and right sides don't agree with each other, and it fails 3 by default. So it's discontinuous, and it turns out the limit also does not exist.
It always doesn't never exist if it's discontinuous.
Nope, because at x equals 1, it was discontinuous, but the limit existed. So the limit is kind of like just part 2 of the continuity test. It's saying, what is it approaching from left and right? Okay, so you could kind of almost boil it down to relating to that one piece. Is it approaching the same number from left and right, and what is that number? And actually, if we look at our definition of limit, it says there is a number L that it approaches. So even if this was approaching infinity from both sides, since infinity is not a number, you would still say the limit does not exist. Okay? So that is a graphical understanding of limits. All right, so it's all about what is it approaching from the left and right, and do they agree? And it doesn't matter if it doesn't exist at that point. So that's one thing I want to point out right here. This part, real important. All right, so that's our graphical understanding of limits. Now it turns out, what do you think happens if I have the limit of a continuous function? So if I have a continuous function, the limit of, as x approaches a, of f of x, what do you think that would equal?
A.
Or f of a, right? Let's see. If a function's continuous at all points, that means that at any one of those points, it's approaching from left and right the value of that point. The limit is going to be part 2 of the continuity test, where it's just whatever number they're approaching from left and right. But if this function is continuous everywhere, it's approaching the value that it is at that point. So whatever f of a is what that would be. Okay, so for continuous functions, finding limits is really easy. So let's do that. Find the limit. So let's find the limit. So let's do this example. Limit as x approaches 3 of, here we go, x cubed minus 5x squared plus 7x minus 10. So, is this a continuous function? All over, because it's a polynomial. All right? So because of that, that means the limit is just going to equal f of 3. So let's just plug in 3. So what is f of 3? That would be 3 cubed minus 5 times 3 squared plus 7 times 3 minus 10. You can skip all this work if you need to and just write the answer. What's it going to be? What's it going to be? 21 minus 10 is 11. I'm going to just cheat. -7 apparently. I always do bad with numbers like that. 45 minus 27 would have been 25 minus 7, 18, and -18, then plus 11 is -7. Yeah, it worked out. Okay. So for a continuous function, super easy. Okay? You just plug in the number, and that's what our limit is. Right? Because it's approaching that number all over the place, right, for that particular point. Now this one's a little bit interesting. What if I want the limit as x approaches pi? Man, that would be sad, approaching pi forever and never getting it. No. Of cosine x over x.
Limit of
Cos x over x. Now, question. Can I do this?
No.
That is like super duper illegal. That is not cosine times x, that's cosine of x. Like you could even like put that in parentheses.
Of is multiplication.
Oh, of is multiplication. You're right. Oh, I guess we can cancel that out. The answer is just cos. That doesn't work, right? Cosine of x. Cosine is a function. So now is this function continuous? Or actually, slow down. Is cosine of x, if it was just regular cos x, would that be continuous?
Yes.
Yes, because that would just be like the little ups and downs, right? It would have been just like, whoa, 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 and that's a continuous function all over the place. Is cos x over x continuous?
Possibly.
Yes.
No, because at one point x equals 0.
At one point, x equals 0, and that function would be undefined, right? So let's actually throw a graph of this up. Let's see how good you guys are at cosine. Let's say I've got pi. I'm just going to throw a really simple graph of this. Oh, actually, you know what? This would actually be a little bit more complicated than what it is. But, because I'd have to divide by the value of pi. I'm going to plug this into Sketchpad. Because I could graph cosine x, and then I could talk about where it wasn't defined, but the x is affecting the shape of the graph all over the place, so that would be inaccurate. Cos x over x. And, wow, that's really bizarre. Actually, I wonder if this is in radian mode. Let me just start with a new one. Bam. Yep. Graph. Cos x. Because I think it'll ask me to put it in radians if I do. And then it'll say, trig function, blah, 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 2 pi radians. And I'll say, sure. There we go. That's awesome. What?
Holy crap, that looks so weird.
Isn't that awesome?
Expand the y-axis so you can see it.
Yeah, it looks like a graph is doing that, like, dance where you, I don't know.
Either way, I think we do agree it looks like Squidward Tentacles doing one of his interpretive dances. Wow. Let's see. So that's what the function looks like. And why is it undefined at x equals 0 like we said it would have been? Because I can't divide by 0, right? So that's why it doesn't exist there.
Can't touch this.
Wow, this is interesting. And actually, as this gets further out, it's going to approach closer and closer to, it's going to be approaching, wow. The y values are going to be approaching 0 over time for extreme values of x, but it's not asymptotic because it's going to keep going up and down and just getting closer and closer to it. Wow. Like throwing a rock into a pond and seeing the ripples, and the ripples get slower and slower in their influence over time, like less and less. But technically, they'd still be there for this function forever. Huh. That's a peculiar function. But anyways, the good news is, well, yeah, this doesn't exist at x equals 0. So it's not continuous right there. However, I didn't ask about x equals 0. I asked about pi. Isn't that great news? Because I asked about a point that it is continuous at, right? We don't care about where it's discontinuous over here. I'm asking about a perfectly good point. So as far as I'm concerned, my previous property applies that at A, this function is continuous. Okay? So that means this is going to just straight up equal f of A again. So that's going to just be cosine of pi over pi. Let's see. Do you guys remember what cosine of pi is? Well, how many degrees is pi radians? 180.
1.
Cosine is -1 at 180 degrees because cosine is the x-coordinate on the unit circle. And at 180 degrees, right, I'll even draw a little graph, why not? What the heck? Right, at 180 degrees, we would be all the way over here. The coordinates would be -1, 0. Cosine is the -1. Whew, good times. So that's equal to -1 over pi. And that's what the limit would also be approaching. -1 pi.
-1 pi.
Yeah, -1 pi. So that's a really cool graph, though. Now, what if I asked what the limit was as x approaches 0? Now it's discontinuous there, and the limit would not exist because these are approaching. First of all, they're not approaching numbers, and they're approaching different not numbers. Yes. So the limit would not exist there. However, sometimes I'll end up asking you to find the limit of a function that doesn't exist at the point the function doesn't exist at the particular point, but the limit does exist. Right? Questions like this. And this is a little bit trickier to do algebraically, and that's what we're going to talk about right now. Let's do an example like that. Here we go. Limits. Behold. So let's find the limit as x approaches 3 of the function x squared minus 9 over x minus 3. So,
It doesn't exist.
is this a continuous function?
No, because
No.
x is 3.
It'll be 0 over 0, which is 1.
Oh my goodness, this is even worse. Not only is it 0 in the denominator, but it would be 0 in the numerator.
So it's 1, 0, and undefined all at the same time.
All right, so now that's the question. What is 0 divided by 0 for
Let's
this
just
problem?
say it's undefined because we have no idea what's going on.
It's 1.
Well, it
0.
is undefined. It is undefined. But I could take the limit of this function as we approach something that will equal 0 over 0. And that's going to be interesting, isn't it? So I could graph this and maybe we'd be able to figure it out. It would be one of those situations where there'd be a hole in the graph. Okay? However, in this case, I can actually do some interesting algebraic manipulation with this. 3 squared is 9. 9 minus 9 is 0. And 3 minus 3 is 0.
So then that's 0 over 0.
So the limit as x approaches 3 of x squared minus 9. What does that factor to become?
9 minus 9.
No.
X minus 3 all squared.
No.
No, x plus 3 times x minus 3.
X plus 3, x minus 3. That's the difference of squares pattern, which becomes the sum and difference pattern.
A squared minus b squared.
And now, what can I do here?
You can divide. Or you can cross.
I can cancel out.
Ninja.
So this function is going to look like
6.
it's going to look like the function x plus 3. However, I'd have to notice just something about the domain right here. The domain still carries the fact that x cannot equal 3. All right, regarding the domain. So this is what the function is. It just doesn't exist at 3. Okay? However, it behaves like this line everywhere else.
Why do you write the limit of x minus 3?
That was supposed to be my approach. Whenever I always think of, who was it on Sesame Street that brushed their teeth like that, where they go, Anyone know? No?
I
Anybody?
don't know.
That's whenever I hear that sound, I'm always like, yep, that's what I think about. And he had just like 2 teeth, but he did a terrible job brushing his teeth too. I wasn't that impressed. But nonetheless, I'm not a dentist.
Like the kid from Daddy Daycare, it's like,
So even though this doesn't exist at that point, it's going to behave like this line, y equals x plus 3, everywhere around that point. Okay? So I'm just going to plug in 3. Okay? Even though I know it doesn't exist at 3.
It's 6.
So that's going to equal 3 plus 3, or 6. So the limit is 6, even though it doesn't exist there. Graphically speaking, let me show you what this looks like. Right, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. So my line is x plus 3, so y-intercept of 3, slope of 1, up 1 over 1, up 1 over 1, up 1 over 1, open circle. So the graph looks like this. So from the left, it's approaching 6. From the right, it's approaching 6. But it does not equal 6. In fact, it doesn't even exist there. It's just a graph with a hole in it. And actually what's sad is if you tried graphing this on a calculator or on Geometer Sketchpad, I'll show you, it doesn't represent that hole there. You would have to be clever enough to know that it doesn't exist there. X squared minus 9 divided by, what was it, x minus 3, right? Yeah. So let's, actually this is still in radians, that's really messed up. So 3 is just a little bit less than pi. But notice that there is no pixel indicating that this doesn't exist at 3. Okay? But it doesn't, just so you know. So beware of that. So that's why you have to kind of be aware of your restricted domain to begin with. So yeah, sometimes there's some algebraic maneuvers that we can do where we can cancel stuff out and we can find what the graph looks like everywhere else except where the domain fails. All right? And that's good enough for us, right? Even though it doesn't exist there, the limit still is 6. All right? So does that make sense a little bit? And then there's worse situations where what if I can't do any of the cool canceling? Well, maybe, what should I do? There's some really cool canceling problems, but let's do this last example. So yeah, sometimes you'll have to factor, you'll have to cancel stuff out, and then you just plug it in, basically. But you guys are experts at factoring and canceling stuff from Chapter 9 of our Math 3 course, of course. So let's do this problem. Find the limit as x approaches 0 of 1 minus cos x over x squared. So this has the problem that it doesn't exist at x equals 0. Bad news. Also, I don't have any cool way that I can cancel stuff out algebraically.
also cosine of 0 is 1, so...
Yep. So it's another 0 over 0 situation. So I could try to graph this and see what's taking place, but I also want to let you know that you can use tables. So in fact, the same table that we used before. So let's define this for us here. What if I've got my numerator is 1 minus, oh dear, I hope cosine works. Whew. All right, I was really scared. I was trying to remember what the Excel function for cosine was. Divided by A3 squared. Okay? So I get ugliness, but that's okay.
You get 0.
And what am I interested in? I'm interested in at 0. And let's analyze this using a chart instead of a graph. We'll do both, but so some of what you can do for these is using a graph when you can't do some canceling stuff out or using a chart. But I want you to kind of understand this idea of limits from all of those perspectives, from algebra, from charts, and from graphs. Okay? So it doesn't exist at 0. Oh, darn. From the left, what does this approach? It appears to be approaching 0.5, right? From the right, what does this approach?
0.5.
It appears as that though it's approaching
Actually, it doesn't.
0.5.
I don't think it's approaching 0.5.
You don't?
'Cause-
0.4999999.
Well, look at these nines. 2 nines, 4 nines, 6
oh,
nines.
I was looking at the X.
Oh, that's why. Okay, right. Yeah, on the X's, it's approaching 0, right? But our Y values are approaching 0.5. So I would say that the limit of this is 0.5, even though it doesn't exist there. So it fails part 1 of the continuity test, but it still has a limit. Okay? Let's look at the graph of this, and I think we might be cool. I'm interested. I really like some of these graphs. These are just like craziness. Let's see if we can get a dancing Squidward.
Do you think we'll need a spreadsheet for any of our quiz, test, or midterm answers?
No. Oh, wow. This is somewhat of a normal distribution graph-ish, is what it looks like. However, it still does have that wobble as it goes far out there. That's craziness, huh? Wub, 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 wub.
Wow.
Yeah, it's got a little bit of like dubstep going on there. It's got some wobble. But yeah, so here's the graph, and you can see that it's approaching 0.5 from the left. It's approaching 0.5 from the right. Graphically speaking, though, this would have a hole right here. It just isn't represented by the software. Okay? So you've got to be smarter than a calculator.
Wait, how do you know?
We know that because if I was looking at this function and I asked you what the domain was, you would have said the domain is the set of all x such that x could not equal 0, because that's when the denominator would equal 0. You would have. You would have. So that's the idea of limits. What are your thoughts? Limits are, they're kind of just like part 2 of the continuity test. Just part 2. In a lot of ways, right? So that's what it looks like from charts. That's what it looks like from graphs. All sorts of stuff. Good times. Well, anyways, Internet, goodbye.